Hello everyone, this is Dilip. In today's video, let's see how to solve linear regression using gradient descent with Python. Earlier, we had already covered how to solve the linear regression with normal equation using Python. In case you missed it, the link for it I'll put in the description. Let's go ahead into today's video. I'm using Google Colab to show you this code. The link for it also I'll put in the description. If you have a Google account, this is free for anyone. You can run your programs in the Google Colab itself instead of downloading all Python libraries and making it difficult to configure everything else. You can leave it up to the Google Colab servers itself. So I have a following test data where X is this much and Y is this much. So this is my input. So I'm considering linear regression problem with only two parameters and one variable. So this will ultimately result in a straight line. So X is 1, 2, 3, 4, 5, 6, Y is 1, 2, 3, 4, 5, 6. And you can clearly see the test data like Y equal to X fits this model. So H of X, if theta 0 is 0 and theta 1 equal to 1, that fits our hypothesis and fits our data very well. So let's just use Python and plot this and see how it looks on a graph. So for the test data, and it looks like this: X is 1, Y is 1, X is 2, Y is 2. So you can see just for drawing a straight line like this, H of X equal to X, that solves our problem. Now we'll see how we'll use gradient descent to solve the same thing. For us, we can look at it manually itself and see how the program does it now. So we have the following test data. Let's create our hypothesis, which is theta 0 plus theta 1x. So let's put a x0 over here. X0 is nothing but it's just 1. So it will automatically, this equation will look like the above equation only. So theta 0 x0 plus theta 1 x1. And we are creating our arrays so that if they are in matrix form, they are easy to work it. So test data I am storing in capital Y. Test result, and this is the test data I'm storing in X. So I'm just printing them out and checking Y dot size because we have 6 parameters, just checking whether the size is correct. And I'm printing also X11 and Y00 just to make sure if I access these variables, I get the correct variables. Now let's proceed with creating our hypothesis function. Our hypothesis is nothing but theta 0 x0 plus theta 1 x1. Same thing I'm writing in a single line of code. So hypothesis function will return this. Now this is the mean square error cost function. So given two parameters theta 0 and theta 1, using our test data capital X and capital Y, this will calculate the mean square error cost function. So as you already know, it is 1 by 2m times summation of square error. So first I'm taking 1 by 2m, where m is the size of the test sample. So I'm just putting m equal to y dot size. I'm taking that 1 by 2m, and the square error I'm calculating. So every time we are adding this square error, we're just iterating over all the test samples and taking the difference of the deviation from the standard data and doing the square of it. Now multiplying this 1 by 2m times that square error, we get the cost function. So that's what. So let's just run this as well. Okay, it's run successfully. Now, just to test out the cost function, since we know the result in advance, which is x0 is 0 and x1 is 1, sorry, theta 0 is 0 and theta 1 is 1, what I will do, I'll just put them in the cost function and see whether the cost function is minimized, whether the cost function approaches 0. So it is 0. Let's put a different value and see what happens. 0, 2 I'll put. It calculates a different cost. So 0, 3 I'll put. As you can see, we are going more away from the final result. We are getting the higher cost. Okay. Anyway, this 0, 3 or something, it doesn't matter because again we'll initialize the theta parameter again. So we'll just leave this. Now this is the major one. So as per gradient descent algorithm, we need to continue updating parameters theta 0 and theta 1 till we go to the convergence. Okay. So the derivative of the cost function with respect to theta 0 will look like this. The derivative of cost function with respect to theta 1 will look like this. So this is the iteration step. Iteration step I'm writing in a, it's also a function where first we are calculating the derivative with respect to theta 0 and derivative with respect to theta 1, and then putting them in an array. And then as you can see, whatever the theta, earlier theta value we are getting, we are subtracting that earlier theta minus alpha times, which is our learning parameter, which is learning rate, alpha times derivative. So as you can see here also, it is earlier theta parameter minus alpha times derivative. Now you can see doing it in vectorized formation, it is, I need not put a for loop to go all the theta parameters. I can just put all my theta parameters in one and calculate the derivatives. And then using a vectorized subtraction in one single swoop, I am able to get the result, the final theta. Again, we will go to the next iteration. Okay. Now let's move on. And this is the final code. Okay, let's run this as well, so that that function can be referenced in our code. So here I am choosing a learning rate. So how I choose this learning rate, because I ran it multiple times. That's why I'm able to choose it, but this fits perfectly fine to our data. So I'm just taking the initial theta value, some 3, 5 randomly. And then I am making it a numpy array. And XA, YA. So these are like for plotting. So after I calculate the values of parameter, I want to plot the cost function such that we can visually see how gradient descent is operating. So every step of gradient descent, whenever we are calculating the cost function we are storing in YA, and theta 1, the parameter which ultimately becomes 1, that parameter also we are storing in XA. So at each step of theta calculation, whatever the theta 1 parameter is there, we are storing it XA. So cost function, whatever we are getting the result, we are storing in YA. So it is like this in the end. We calculate at every step, we calculate our theta values using the derivative of the cost function, and then put those theta values in the cost function and see if it converges. Converges is nothing but is it becoming close to 0 or similar, like whether it is value is getting reduced. So based on our plotting, we can see whether our gradient descent is working properly or not, and then we can alter our learning rate as required. And one more thing is even feature scaling is also important. So it not be like always the learning rate is the problem. If our gradient descent cost function doesn't optimize, it can be that our features are not scaled properly. So in my earlier videos, I will talk more about how to do feature scaling, etc. You can watch those videos as well. So XA append, Y append is nothing but just for plotting the graph. I'm appending the values to here. So whatever the cost function is there, at every step, I'm calculating the cost function. And at every iteration, you can see we are doing this call to the call next step, which is nothing but it will calculate our next theta values. So I'm putting them into cost function and checking whether cost function is getting optimized. And if our cost function, so this is my convergence rule. So if our cost function becomes less than 10 to the power of minus 5, so it is of the order of e to the power of minus 5, then I'm doing a break, like don't do more iterations. The iterations are enough. Otherwise, I'm just printing the iteration number also along with the result. So I'm doing this for 300 iterations. If in between our cost function optimizes to 10 to the power of minus 5, which is like close to 0, our this for loop will break and we'll get the final theta values getting printed. Okay. So I'll run this as well and see our gradient descent algorithm in action. So you can see it has run, completed all the iterations. So it has run for close to 250 some more iterations. I'll show you. So in the first iteration number 0, our cost is 140. And theta 0, theta 1 values are 0.96 and minus 3.54. And in the second iteration, our cost reduced. And our theta 0, theta 1 parameters are 2.7 and 4.3. So as you can see, the cost is reducing for every iteration. So it means our whatever the test data is there, as well as our learning rate, whatever we have put, it is appropriate. So cost function reduces. And as you can see, once we reached the, let me just scroll this up. Once we reached the 236th iteration, it has become close to 10 to the power of minus 5. So it has stopped the algorithm from running further. And you can see theta 0 is close to 0 and theta 1 is close to 1. So it means we have reached our correct result as required. Now, using these values, if we plot the cost function versus theta 1 parameter, because theta 0 is 0, and if you use theta 0 as well, the graph we need to put in some 3D format. That's the reason what I will do is I'll just take the theta 1 parameter and see how its value is determining the cost function. So let's just plot it and see. And you can see the initial value we had was the cost function is 140. Even I'm printing the initial value and final value of the cost function, and the initial theta 1 and the final value of theta 1. So initially our cost function is close to 140. Then you can see our gradient descent, how it optimizes. It has come like this. Ultimately, it has reached the global optimum. And it has reached the global optimum when theta 1 is 1. So it is here. And also you can see this, our cost function is a nice parabola now. You can see a nice parabola here. Okay. And one more thing is, it's a parabola as well as the cost function is nearing to 0. So let's see if we change the learning rate, what happens. Let's give some random So let's give say some 20. Okay, let's see what will happen. So it has encountered some overflow, maybe because you can see the class flow function became 10 to the power of 17. And let's plot this and see how is the data till now with respect to theta 1. You can see how the cost function looks like. So unless the cost function is a nice parabola and you can see it getting optimized, you can consider avoiding the other alphas. And feature scaling is also important as well, since our features are already scaled well because they are the order of between 1 to 10. Our features are also scaled well. And if we have more number of variables, then all those variables should be on the similar scale. If they are between 1 to 10, all of them should be between 1 to 10 or similar, between maximum 1 to 20. It should not be like one is in the tens and other one is in the thousands, or one is in the tens and another one is in the microseconds. It should be within the same range. And as you can see, how the cost function is changing. So if I put a okay, let's just put 0.025 and see. Anyway, like I'll not go deeper and waste your time. So if you want, you can experiment on this. The link for this I'll give in the description, and you can experiment, you can copy, you can run this code and see how the cost function is getting changed. Now, one final thing is, instead of choosing the learning rate alpha, you can use other optimization algorithms which are similar to gradient descent and which run much faster, but which are complex to explain. So these are conjugate gradient and LBFGS. If you have a cost function and the derivative, you can plug them into these libraries and get the result. Details about them is beyond the scope of this discussion. So I'll leave that up to you to experiment. Thanks everyone for watching the video. Bye.